My name is Graphics. Today we want to study another aspect of electromagnetism, which is called the magnetic circuit with air gap. What we've been doing in our previous video has been magnetic circuit without air gap, right? But today we want to study the magnetic circuit with what? Air gap. Now let me show you the difference between the one without air gap and the one with air gap. Now let's see. Now this is how the diagram is for a magnetic circuit with what? Without air gap, where this is called the N, which is our number of turn, and this is our I current, right? And this is what? The core. Is that taken? Now let's now see, in this case we can easily say that what? Our reluctance X or R is equal to what? The length over what? Our U naught UR times area. This is what we have in terms of reluctance, right? Now let's see without air gap. Let's see with air gap now. Now this is the magnetic circuit with air gap. Now when you open here up, the distance between each magnetic surfaces is called our LG, right? So I can easily type that my reluctance, it can be R or X, is equals to what? That will be L all over what? U naught URA, right? Plus L all over what? U naught. Then we have what? The A. Because this is the length of the air gap, and this is the length of, it can be an iron core or the metal, so we'll call it, this is basically one material throughout. It's not composite. But here now involve the material plus what? The air gap. But the air gap, air has a relative permeability that is negligible, so we just use the relative our absolute what? Permeability, right? So now what is this air gap that we're talking about? Now we say that an air gap, right, is the volume of air between the two magnetic surfaces. This is the surface here and this is the surface here, right? And the length of the air gap is equal to what? The distance between these two surfaces. So, now one of the usefulness of the air gap is that when there's no air gap, most times, right, we usually have excessive flux produced by high level current in the windings. So to reduce the excessive flux produced by high level current in the winding, we use air gap. And also the air gap helps to prevent saturation. It helps to what? Prevent saturation. Now let's move forward. We know very well that MMF is equals to what? IN. That is, our magnetomotive force is equals to what? IN, right? And let me call this equation 1. And also we know that from magnetic field strength equals to what? IN over what? L. If I make my IN, so the formula because multiplying, we'll be having HL equals to what? IN. So anywhere I see my IN, I'll put what? My HL. So let me call this equation 2. So I'll write that substitute IN equals to what? HL in equation 1. So if I put it here, so I will not say therefore my MMF will now give me what? HL. Right? Now also, I'll call this equation 3 just to recognize them. We know very well that my magnetic flux density B is equals to my permeability multiplied by what? My magnetic field strength. If I make my H the sort of formula, I'm going to have H equals to what? B over U. That is my magnetic field, my magnetic flux density over what? My permeability. Right? Now, let me put this from B equals to this. I'll call it my equation what? This is equation 3 here. I'll call it equation what? Equation 4. IV. So I will substitute H equals to what? B over this in equation 4. So if I put it in my equation 4, so I will now say that what? Into equation 3, into equation 3, this equation 3 here. So I will now have that my MMF is equals to, so me putting my H, I'm going to put what? My B, right? And I'm having L close to it, all over what? The U here, this is what we're having. So instead of H, I'm putting B, this times the L. So we're having that my MMF is equal to what? BL over what? U. Where my B is called magnetic flux density, my L is the length of the material, and my U is called permeability. So I'm going to write that my B is equals to what? Flux density, right? My L is what? The length in meter of the material. Then U is given as what? Permeability. So it's given as 4 pi times 10 to the power minus 7 ampere per what? Meter. So whenever you are told to calculate MMF, another name for MMF, since we have MMF is giving us MMF is giving us current times number of turn, and it can also be called AT, that is what? Ampere for current, and TN for what? For turn. So I can also write that my AT is equals to what? BL over what? Dix. So please, this is very, very important. We are going to use them, and this is also very important when dealing with composite materials, right? And this also, we've done it in the past in our previous video. Now let's take an example and see how we can apply this formula. Example 1 said, find the MMF of an electromagnet that has an air gap of 4 mm and a flux density of 1.3 Weber per meter square. Like I've been telling in my previous video, the first thing whenever you are seeing calculations like this, you need to write out your data or your parameter. So my data given, we say the air gap, we'll call it LG, is given as what? 4 mm, right? And also we are given the flux density B to be given as what? 1.3 Weber per meter square, right? Now we need to make the unit conform. And also apart from that, since we're talking about air gap have absolute permeability or permeability due to free space to be equal to what? 4 pi times 10 raised to the power minus 7 ampere per meter. Now we need to make everything conform. I need to convert 4 millimeter into meter. So I'll divide by 1000. So I'll have 0.004 meter. Right? Now after doing that, I'll recall we're looking for MMF. For my formula, we say that my MMF can either be BL over U, or we'll call it AT equals to BL over U. So what I'm actually going to do here is this. I'll say recall my MMF in terms of air gap is equals to the flux density times the length, but this time is length of the air gap, all over permeability. Right? Now this will now give me if I move forward, this will now give me my B is giving us 1.3 multiply the LG is what? 0.004 all over 4 pi times 10 to the power minus 7. 4 pi times 10 to the power of what? Minus 7. So therefore my MMF will now give me, we have 4.138 ampere ton, 80, right? You can call it 80 or 8, that is the MMF here. Example 2. It says an iron of mean length, an iron ring of mean length 50 cm has an air gap of 1 mm and winding of 200 tons. If the relative permeability is 300, find the flux density when the current of 1A is flowing through. Now the first thing you have to, like I said earlier, you need to put out the parameters, right? So the data given here, we have the length of the iron ring, which is Li, and that will give me what? 50 centimeter, right? 50 centimeter. If I convert it into meter, I'll be having 0.05 meter. Now the next thing we are given here is the length of the air gap, LG, and that will give me 1 millimeter. And if I convert it into meter, I'll divide my 1 by 1000. I'll be having 0.001 meter. Now the number of ton of the winding is N, and that is giving us what? 200. Also we have the permeability, relative permeability, which is giving us mu r, and that is 300. Now it says we will find the flux density B, and we don't know that, but the current given here is 1A, as in 1 amp. So my current I is giving us what? 1 amp. 1 amp. So what we actually do here is, we know that in terms of a magnetic circuit with air gap, we say that my MMF is equals to what? My MMF is equals to IN, right? My MMF is equals to IN. So since we have the MMF of the air gap and also the MMF of what? Of the iron ring. So now say that my MMF total is equals to what? MMF of the what? Iron ring plus MMF of the what? Air gap. So with all what we've done in our previous example, we will say that what? My MMF, since I'm saying ampere ton, which is equals to or I will say ampere ton since I'm saying IN, right? And that will give me, we have BLI all over what? All over mu, that is permeability, plus BLG all over what? Permeability. And that is this is U not UR, because giving the density of B U not alone. Now if you factorize, my IN will be equals to what is common. I have B common here. I have what? U naught common also. Into brackets, we have Li over UR plus what? LG. Don't forget we are looking for B. Now if I impute all my value, we know very well that I have I. My I here is given as a current, and that is 1. Multiplied by my number of turn is 200, right? Equals to the B over 4 pi times 10 raised power minus 7, which is given, this is a constant, into brackets. The Li, length of the iron ring, is 0.05 all over the relative permeability, which is what? 300, and the length of the air gap is 0.001 plus 0.001. So this is what we have. Now from here, 1 times 200 is 200. I'm taking this up here, so say 200 multiplied by 4 pi times 10 raised power minus 7 is equals to B into brackets. We have 0.05 all over 300 plus 0.001 close the bracket. Now if I multiply 200 times this, what will I have? This will give us, we have this to give us 2.51, 2 points times 10 raised power minus 4 equals to B into brackets 0.05 divided by 300, 0.05 divided by 300, that will give me 1.667 times 10 raised power minus 4 plus 0.001, right? So plus 0.001, and that will give me 1.167 times 10 raised power minus 3. 1.167 from here we have, first of all, we have 2.51 times 10 raised power minus 4 is equals to B into brackets 1.1667 times 10 raised power what? Minus 3, right? Now if I divide both sides by this, I'll be having 2.51 times 10 raised power minus 4 all over 1.1667 times 10 raised power what? Minus 3, and that'll give us what? B. So if I do that, I'm going to be having this. So we have B is equals to what? 0.215 Teslas. So that will be our answer. So if this video has been very helpful, don't forget to click on the subscribe button.